All right, folks. Um, so I want to talk just for a few minutes about the launch portion of your project and mainly the chemical part of the launch portion of the project, because we haven't really talked that much about the chemistry of it. The chemical equation that I have here, 2KNO3, that's potassium nitrate, plus sulfur, plus carbon, which could be like charcoal or something like that. Um, that equation, the 2KNO3 plus sulfur plus carbon, that is the formula for black powder. And that's the motors that we're using in our rockets are black powder. Okay. So that's the formula we're using for black powder. That is actually, you can vary it a little bit, but that's the main formula. When we burn it, or when we light those on fire, that is this indicated by the arrow right here. Oxidation is occurring. We're burning it. And this side is what happens. So we end up with 2Ks. That's potassium sulfate, or not sulfate, but potassium sulfide. This right here is where most of the smoke comes from and the smell, because we smell that sulfur acrid smell, and it's that black smoke comes from that. Okay. The energy you'll see in a second mainly comes from this N2 right here. Okay. And the whole process gets started mainly by this um, burning of the carbons, combining them with the O3 over there. That's the sort of the catalyst that gets everything rolling. So here's kind of what happens in the um, in the process. Okay, so we light this on fire. We combine this carbon with these oxygens, and we create this right here. This is exothermic. When these are broken apart, all these bonds are broken apart. It takes energy to break those apart. That energy comes from the lighter that we use to light the fuse. It comes from the fuse as the fuse is burning. It gets the first couple things breaking apart. It breaks these bonds apart. It takes so breaking bonds takes energy. So you have to put energy in to break bonds. So to break a molecule apart, it takes energy putting in to break it apart. So putting together, so put together, not writing this very well, bonds gives off energy. So we broke apart this stuff up here, the O3 and the carbons, and we put them back together as this. When we put them back together, that's when they gave off a little bit of energy. That little bit of energy is used to further break down the KNO3. And when those come back together, this gives off a tiny amount of energy, but the N2s come back together and they form the nitrogen triple bond. The nitrogen triple bond, usually we denote that in chemistry with an N, then another N, and then one, two, three here. Okay. So the nitrogen triple bond is the strongest bond that we've ever found. It's the strongest bond in nature. Um, but what that means is I equate it to sort of having handles on a box. The more handles you have on a box, the less energy it takes for you to lift the box. So if there's no handles on this heavy box, it takes a lot of strength for you to grab onto that heavy box and to hold onto it so it doesn't slip out of your hands. If you have one handle, it's a little bit easier, but it still takes some energy. Two handles is a lot easier. Three handles is a piece of cake, right? So it takes very little energy for these to come together. Okay. It takes very little energy for them to stay together. to hold together. And because of that, right here, when they do come together, all this energy they needed to exist separately over here can go away. And when it goes away, we call that an explosion. There's lots and lots of energy that's given off because it takes very, very little energy to stay together. Ironically, it takes lots and lots of energy to break this bond apart, too. Even though it takes it very little energy to stay together, it takes a lot of energy to break it apart. That's why we breathe in nitrogen all the time. 78% of the air is nitrogen. We breathe it in. We can't do anything with it. We don't have the energy to break apart those nitrogen bonds. We breathe it in, breathe it right back out. Nothing happens. It's basically inert to us because we can't break those bonds. We don't have the energy. But um, as these bonds are created, it gives off tremendous amounts of energy. That energy is what I'm going to draw a little rocket over here. Very poor rocket right there. So that energy is directed by pushing think of it as like the barrel of a gun. It's shooting downward. All of the debris, the smoke, the particles is shooting downward out the back of the rocket. And as it does that, when you shoot a gun, especially a heavy gun, you know that anybody who has shot a gun knows that the gun kicks, right? Because for every action, there's an equal and opposite reaction. That's one of Newton's laws. So as it's shooting all of that debris downward, um, it's shooting all of this stuff downward. It's also pushing the rocket upward. Okay. And it's counteracting the forces of gravity pushing downward. So it's pushing down against all of these molecules and bits and pieces and smoke, pushing down against those. Like we walk on the floor, we push down on the floor. The rocket's pushing down on all these particles and giving itself the energy to push itself up by using mainly that nitrogen triple bond. So I would encourage you to look up any explosive that you can think of, from plastic explosives, so-called plastic explosives, to TNT, like dynamite, or any type of explosive you can think of. All of them will have any conventional explosive, not like nuclear explosive, but any of the conventional explosives will have a significant nitrogen portion to it because all of them use that same triple bond feature to come up with all of that energy. Because that's where we get the most bang for the buck when it comes to um, chemical energy. We can get more chemical energy out of creating nitrogen triple bonds than anything else. So that's sort of what's happening there. Hopefully you understand that. That's like part of your, like, where is this chemical energy coming from? And what's going on. The other part of this is the physics of it. And I kind of alluded to that. You're pushing down on, you're shoving all these particles out of here. So you're pushing down on all these particles really, really fast. They have a really, really small mass, but you're pushing them really, really fast. So a lot of those particles are leaving out the back of the rocket um, at faster than the speed of sound, like Mach 2 maybe or 3. They're at really, really high speeds, but they're really, really tiny particles. And that is offset by the heavy rocket, heavy compared to those particles, moving at a much, much slower speed going upward. So it overcomes the rate of gravity to begin with, and then it begins accelerating up from there. So I'm going to leave you with that for now. Hopefully that helps you as you're beginning to put together